Hi, everyone. So in this video clip, I just basically want to discuss ionic compounds. And ionic compounds are molecules that are formed by elements that form negative and positively charged ions. Before we can do that, we really need to recap why elements form ions. And the reason for this is so that they have full valence shells. The thing that we need to remember is that our group 8, which are our noble gases, are always they're always found as an element, and they're never found as compounds because they have a full valence shell. What they have is they have 8 electrons on their outermost shell. So if we're looking at example neon. So neon has 10 protons, and it has 2 shells. The first shell has 2 electrons. And remember, our first shell is full at 2 electrons, and our second shell, which in this case would be its valence shell, is full at 8 electrons. So whenever an element is forming an ion, it's trying to get to the same configuration of electrons that noble gases have. And that configuration is that it has a full shell. And in this case, our full valence shell is our magic number of 8. So we have an example here. This is neon. So we need to also remember that metals will lose electrons to get a full last shell. So metals will lose valence electrons. So let's look at an example of sodium. So if we're looking at sodium, sodium has 11 protons. The first shell has 2 electrons. The second shell has 8 electrons. And its third shell, because again, sodium is in period 3. So third shell. And because it is in the alkali metals, so group 1 has 1 valence electron. So we'll draw the valence electron right here. So what I've drawn right now is the sodium atom. So again, the sodium atom, 11 electrons and 11 protons. Now, when sodium forms a chemical reaction, it loses this last electron on its valence shell. So it basically becomes an ion. And metals, whether they're in groups 1, 2, and 3, are going to lose this valence electron. So what would happen is that sodium would be giving this electron to another element that needs electrons. So if this electron disappears, well, the entire shell disappears. So the entire shell disappearing. And we'll notice that what we have right here is ionic sodium, Na plus 1, because I have 1 more proton, 11 protons, compared to all of my electrons, 10 electrons. But we can see that it now has a full shell. And it now has the same electron configuration of its nearest noble gas, which is neon. So metals will lose valence electrons. So this is going to be group 1, or alkali metals, group 2, or alkaline earth metals, and group 3. Nonmetals are going to gain valence electrons. So let's look at fluorine. So fluorine is a nonmetal. It's in group 7. It'll have 9 protons. It has 2 shells. The first shell has 2 electrons, and the second shell has 7 electrons. Now, in this case, fluorine needs to add electrons to get a full valence shell, because right now, fluorine has 9 protons, 9 electrons, and 7 electrons on its last shell because it's in group 7. So to gain a full last shell, it needs to add electrons. So if we add an electron here, it now has a full valence shell. And its overall charge here would be F minus 1 because I've added an electron, because we need to remember electrons have a negative charge. So if I add more electrons, I'm becoming more negative. When I remove electrons, I'm becoming more positive because my protons never change. So if I'm removing electrons, I have more protons than electrons. And we can see that fluorine has the same electron configuration as its nearest noble gas, which is neon. So when elements are losing and gaining electrons, they're actually forming a chemical bond. In this case, they're forming an ionic bond. And that's where we actually have these ionic compounds due to elements gaining and losing electrons. So again, metals will lose your valence electrons, and these would be anything in groups 1, 2, and 3. Nonmetals will gain valence electrons. So this is going to be groups 5, 6, and 7. Noble gases are not forming ions because they already have that full valence shell. So let's do an example of sodium and chlorine. So what I'm going to do is I'm actually going to draw the Lewis dot diagrams. Now, the Lewis dot diagrams are very useful because remember, Lewis dot diagrams show the electrons on our last shell. So this is where your periodic table is your best friend, and it should be right next to you all the time. So sodium, our symbol is Na, and it has 1 valence electron, so 1 dot. Chlorine, so because it's in group 1, it's our alkali metal. Chlorine is in group 7, so that means it has 7 valence electrons. So chlorine, 1, 2, 3, 4, 5, 6, 7. Now, if we're looking at our formation of the compound, we have sodium with 1 valence electron, chlorine with 7 valence electrons. Chlorine needs an electron to get a full last shell. Sodium needs to lose an electron to get a full last shell. So what happens is the electron leaves sodium and goes to chlorine. So as a result, the ion that is formed is Na plus 1, because every single time I lose an electron, I become more positive. The ion that is formed with chlorine would be Cl minus 1, because the electron that left sodium went to chlorine. So if I look at my overall charge of my compound is actually neutral because the electrons from sodium, so the E from sodium, went to chlorine. So the compound that is formed is sodium chloride. Let's do another example. So we have beryllium and we have oxygen. So if I look on the periodic table, beryllium I can see is in group 2. So it is an alkaline earth metal. Oxygen is in group 6. So beryllium, group 2, is going to have 2 valence electrons. Be with 2 valence electrons. Oxygen, because it is in group 6, is going to have 6 valence electrons. 1, 2, 3, 4, 5, 6. Let's draw it. Not that way. Sorry. 5 and 6. Because remember, when we're doing our Lewis dot diagrams, we always put our first electron in the north position, then the south, then the east, then the west, then we buddy up. So if I'm looking at this right here, I see beryllium has 2 electrons to give up. Oxygen has 2 electrons it wants to take. So what happens is what we think is going to happen. 3, 4, 5, 6. That the oxygen will take the 2 electrons that beryllium wants to give up. So as a result, the ionic charge for beryllium is Be plus 2 because it lost 2 electrons. The ionic charge for oxygen is going to be O minus 2 because it gained 2 electrons. So the molecule that's formed, the compound that's formed, is beryllium oxide, Be and O. So, and this is the reason why if we're looking at our compound names, the metal always goes first because it is the element that is losing electrons. The non-metal always goes second because it's the element that is gaining electrons. So our first 2 examples we saw, it was pretty straightforward. It was one element is losing all their electrons and the other element is gaining all their electrons. But this is not the only situation that can happen because we also have to realize that we have to look at the net number of electrons that are being lost and shared. And in some cases, and this is where we have, molecules where I have, why is something like lithium oxide has 2 lithiums and 1 oxygen? It has to do with the number of electrons that are being shared, being given and taken. And that's what we're going to be looking at next. So we have aluminum and we have chlorine. So if we're looking at our periodic table, aluminum is in group 3. So that means it's going to have 3 valence electrons. So aluminum, group 3, 1, 2, 3. But looking at chlorine, chlorine is a halogen. So that is group 7. So that means it is going to have, yep, you guessed it, 7 valence electrons. 1, 2, 3, 4, 5, 6, and 7. So aluminum needs to lose all 3 of these valence electrons, and chlorine is going to be gaining valence electrons. Now, this is where we need to look at both elements. Chlorine has only space for 1 electron. So it can only accept 1 electron from aluminum. So chlorine, this guy, he's happy because he now has a full shell. But the aluminum is not happy because it has 2 more electrons it wants to lose. And the reason why it wants to lose, because remember, it's trying to get a full last shell. So it's an all or nothing thing. You can't have some having partial electrons on their valence shell. No, it needs to lose the entire valence shell for metals. And for the nonmetals, it needs to gain all those empty spots to look like the noble gases that have a full last shell. So if we're looking at aluminum, the only way that aluminum can lose these 2 valence electrons is if there comes 2 more chlorines, and that each chlorine takes 1 electron each. So that means this chlorine can take this electron, and this chlorine can take this electron. So now I have 3 chlorines that are each taking 1 electron from the aluminum, and I have 1 aluminum that has given up 3 electrons. But we need to remember that if we look at our compound, I have 1 aluminum and I have 3 chlorines. And this is where our subscript comes into play when we were looking at our different compounds. That when we're looking at our compounds, why do I have some compounds that just have 1 element? Why do I have some compounds that have 3? For this right here, because aluminum has 3 electrons that it needs to get rid of to get a full last shell. But each chlorine can only take 1 electron. So to form aluminum chloride, I need to have 3 chlorines to each accept 1 electron. And we have to realize that our overall compound is neutral. I have aluminum that's given up 3 electrons, but I have 3 chlorines that's each taken 1 electron. So all the electrons from aluminum were distributed into those 3 chlorines. Let's do another example. Lithium and phosphorus. So if I look at my periodic table, lithium is an alkali metal. So that means it's in group 1. So lithium will have 1 valence electron. Phosphorus, it is in group 5. So that means it is going to have 5 valence electrons. 1, 2, 3, 4, 5. So if we're looking at this, we know that we have a lithium and we have phosphorus. Lithium has 1 valence electron that it can give up. So that means lithium is only have that 1 valence electron on its last shell that it can give up. Phosphorus has places for 3 electrons. So what has to happen here is that there needs to be 3 lithiums. And each lithium is going to be giving their valence electrons to phosphorus. So our ionic charge, well, lithium is going to be Li plus 1. Phosphorus, because it gained 3 electrons, is P minus 3. And if we look at our molecular formula, well, if we look at it, we have 3 lithiums and 1 phosphorus. And for every single lithium, so I have 3 lithiums that each gave up 1 electron. Where did those electrons go? To the phosphorus. So my compound is neutral overall because the electrons from one went to the other. So lithium phosphide. The moral of the story is that my atoms, when they're forming ions, are losing their valence electrons if they're metals, gaining valence electrons if they're nonmetals, so that they all end up with a full valence shell. When we're forming molecules, the metals give up their electrons and give it to the nonmetals, because my metals, again, are in groups 1, 2, and 3. My nonmetals are in groups 5, 6, and 7. We're going to do one more for good luck. So we have barium, which is an alkaline earth. So that means it's in group 2. So barium will have 2 valence electrons. Arsenic is in group 5. So that means arsenic will have 5 valence electrons. So if we're looking at this right here, so we have barium, we have arsenic. Barium has 2 electrons, it can give up. Arsenic has spots for 3 electrons. So barium gives up 1 electron, gives up 2 electrons. Barium's happy, it's given up its electrons, it has a full shell. But arsenic is not. It's missing 1 more electron. So what needs to happen? Another barium has to come in. So another barium comes in. This barium gives its electron to arsenic. Now arsenic's happy, but barium's not, because it still has 1 more electron it can give up. So what happens? An arsenic comes in to start taking those missing electrons. So arsenic comes in, takes an electron from barium. So this barium's happy, but arsenic's not happy because it's missing 2 electrons. So what needs to come in to give arsenic those 2 extra electrons? Another barium. So another barium comes in to give arsenic those 2 electrons. Now barium's happy. It's given up all of its electrons to have full last shell. Arsenic's happy. It's taken all those electrons to have a full last shell. So if we're looking at our charges here, barium is Ba plus 2, and arsenic is As minus 3. Now, if we look at this, I had 3 bariums, and each barium gave up 2 electrons. So that means my barium in total gave 6 electrons. My arsenics each had spaces for 3 each. So that means my arsenic in total took 6 electrons. So that means the total electrons that all of the bariums combined gave went to arsenic. So my compound is neutral. And if we're looking at the chemical formula of my compound, well, I needed 3 bariums to give up my electrons to 2 arsenics. So my chemical formula would be barium arsenide. So I hope this helps. And the key thing that we need to remember is that our metals, which are in groups 1, 2, and 3, will lose electrons to have a full last shell. Our nonmetals, which are in groups 5, 6, and 7, will gain electrons to get a full last shell. And when we're forming our ionic compound, the total number of electrons is constant in the sense that all of the electrons that the metal loses, the non-metals gain. So I hope this clarifies our ionic compounds a little bit more, and I hope that you have a great day.